So after doing a video on galvanic cell setup, I thought it would be a good idea to walk you through a free response question on electrochemistry. So let's take a look at it. Metal air cells are a relatively new type of portable energy source consisting of a metal anode, an alkaline electrolyte paste that contains water, and a porous cathode membrane that lets in oxygen from the air. A schematic of the cell is shown above. Reduction potentials for the cathode and 3 possible metal anodes are given in the table below. So let's see what it's asking us. Early forms of metal air cells used zinc as the anode. Zinc oxide is produced as the cell operates according to the overall equation below. So what we need to do is calculate the cell potential for the zinc air cell. Now, we have to remember that cell potential is cathode minus anode. Okay, now to effectively use this, we have to go back and look at our cell and see which things are at the cathode and the anode. So it already points out to us that oxygen is at the cathode. And what else do we need? We need zinc. So we have the oxygen part at the cathode, and all we need is zinc. So I'm going over here, and I see the reaction for zinc, which is the second one. So zinc must be at the anode. Alright, so now it's cathode minus anode. We've already said that oxygen is at the cathode, so we go over here, we see that this is the half reaction with oxygen. None of the other ones have it, and it's positive 0.34. Now we subtract the anode, which is zinc, and that says negative 1.31. So minus negative 1.31. And that's going to be about 1.65 positive. Okay? So we've answered this part. Now it's asking, the electrolyte paste contains OH- ions. On the diagram of the cell above, draw an arrow to indicate the direction of migration of OH- ions through the electrolyte as the cell operates. Okay, so let's go back and look over here. So it's asking us what direction the OH- ions are going in. And OH- ions are negative, so they're going to want to go towards the direction that's more positive. So we see here that there's a electron sign, and it says that the direction is going this way. So you can just visualize that the electrons are going from this way into this wire and into the cathode. So that means that negative electrons are escaping the anode into the cathode, meaning that there's going to be a positive buildup over here and a negative buildup over here. So let's go back to what it's really asking. Draw an arrow to indicate the direction of migration of OH- ions. Okay, so that's easy. We just said that this side is going to have a positive buildup and this side is going to have a negative buildup. So it's going to go to the left. A fresh zinc air cell is weighed on an analytical balance before being placed in a hearing aid for use. As the cell operates, does the mass of the cell increase, decrease, or remain the same? Okay, so if you have no idea how to answer a question the first time you read it, I would say to look at the next question, because that might give you a hint of how to answer the question before. So it says, justify your answer to part B1 in terms of the equation for the overall cell reaction. It's saying right here, in terms of the equation for the overall cell reaction. So that's giving us a big hint right there. We need to use this equation. So does the mass of the cell increase, decrease, or remain the same as the cell operates? Well, as it operates, zinc and oxygen combine to create zinc oxide. So it's basically pulling oxygen molecules from the air and creating zinc oxide. And I would say that the oxygen is adding mass to the cell because it's going to create this, which is going to increase the mass. So you've already answered these two parts at the same time. The mass of the cell increases, and the justification is because zinc oxide is created, and the addition of oxygen will add mass to the cell. Okay, next part. We have the zinc air cell is taken to the top of the mountain where the air pressure is lower. Will the cell potential be higher, lower, or the same as the cell potential at the lower elevation? Okay, so let's think about this. We have a mountain, and we're taking the cell up to the top, and air pressure is lower here, and air pressure is higher here. Okay, let's remember that. So will the cell potential be higher, lower, or the same? Now, going back to the equation, we see that we need oxygen for the cell to function. And that has to deal with cell potential, because the higher the cell potential, the more effective the cell is going to work, and the more effective it's going to function. So at higher elevation, there's less air pressure, meaning that there's less oxygen, right? So if there's less oxygen, then that means the cell potential will be lower than at a lower elevation, because at a lower elevation you have more oxygen to work with. Therefore, the cell potential is higher here compared to here. All right. Part D. Metal air cells need to be lightweight for many applications. In order to transfer more electrons with a smaller mass, Na and Ca are investigated as potential anodes. A 1 gram anode of which of these metals would transfer more electrons, assuming that the anode is totally consumed during the lifetime of a cell. Justify your answer with calculations. So it's asking us to compare sodium and calcium. Okay, so I got a periodic table, and we see that sodium is over here, calcium is over here. Now, it's asking us which one would transfer more electrons. Now, we see that Na is here, meaning that if it loses one electron, it'll become an Na plus ion. But Ca needs to lose 2 electrons for it to become an ion. So we have Na plus and Ca2 plus. So we have 1 gram of Na, and we need to convert this to electrons somehow. So we say that there's 1 electron being transferred for each mole of Na. So what we need to do is multiply this by the molar mass to convert it to moles. Then we can convert that to electrons. So here it's about 23 grams per mole. So these now cancel out. And for every 1 mole of Na, we have 1 mole of electrons being transferred. So that's going to be 1 over 23, which is about 0.043 moles of electrons. Okay, so now we need 1 gram of calcium. We also multiply that by the molar mass, which is about 40. So 40 grams per mole of calcium, and every mole of calcium transfers 2 moles of electrons. And now we have 2 over 40, which is 0.05 moles of electrons. So obviously calcium transfers more electrons. So we've basically already answered this whole question, and we've justified our answer with calculations. Now, last part. The only common oxide of zinc has the formula ZnO. Write the electron configuration for a zinc atom in the ground state. Okay, back to electron configurations. Let's look for zinc first in the periodic table. I see it right here. So remember that you can use a shortcut for this. So what you do is go to the nearest noble gas, which is argon. So you put the noble gas in brackets, and then we go here. This is the fourth row in the S shell. So that's 4s2. And then we have the 3d here. So that's going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 3d10. So that's it for the electron configuration. And then it's saying, from which sublevel are electrons removed when a zinc atom in the ground state is oxidized? So oxidation is when you lose electrons. Don't forget that. So when you lose an electron, it's going to come out from the outermost energy level, which is 4, because 4 is greater than 3. So we say that it's going to come out from the 4s sublevel. And we've basically answered all of this free response question.